So this will be the last lecture. Next week will only be for revisions. And I'm going to talk briefly about this part of learning representations and transfer learning too. So the idea here, I'm not going to go into much detail, just a brief introduction, but the idea is that features are very important for machine learning. So if you have the right features, it's easy to get to the right answer. If you start with the wrong features, then it's very hard. For example, you can see the difference between trying to do simple algebra with Roman numbers, for example. It's very hard. If you use these Hindu-Arabic numbers that we use, it becomes a lot easier. So if you have the right features in machine learning, you can solve the problem much easier. And we can think about deep learning as having a huge network to learn the right features, and then we have a linear classifier at the end that just decides what the class is or predicts the value. So the last layer of the network is just a linear classifier that receives exactly the right features to solve the problem. So this brings us to this idea of trying to learn the proper representation of the data. If we try to do this with supervised learning and few data, so a small data set, then this can lead to overfitting. And this is usually a problem because for supervised learning we need labeled data, and labeled data is usually more expensive. So usually we can try to learn the best representation with unlabeled data, which is generally more abundant, and then use those representations to help us find the right features to solve a problem. So this is a general approach of trying to learn the best representation independently then of the actual supervised learning problem we're trying to solve. So let's start with one way of doing this. This is nowadays mostly for historical interest, but still can be used in some specific cases. And the idea is to use this greedy, layer-wise, unsupervised pre-training. The greedy because we are using one layer at a time and trying to train it as well as possible before adding the other one. So this is the kind of greedy search that we find in many algorithms. We're trying to optimize at each step, even though perhaps the global optimum cannot be reached in this way, but this is one feasible path through the possibilities. Layer-wise, because we're training one layer at a time. So basically, if we try to train a complete network at once, it's a lot more work and a lot harder than just to train a small network with one hidden layer. And the idea here is, this was before the rectified linear unit, so before 2015 or something like that. If we use sigmoid activation, it's very hard to train deep networks. And so what they started doing was to train an autoencoder with unsupervised learning with only one hidden layer. And then after the autoencoder trains, we throw away the output layer and we use the hidden layer representation as an input to the next layer. And we train a new autoencoder with only one hidden layer. And then we keep stacking those autoencoders. Typically they were denoising autoencoders so that they could learn more useful representation. And each layer could be trained with unsupervised learning. And it was just training to output the same as the input, and the input was the output of the previous layer. So then everything stacked and fit together. And this worked fairly well because we could train a network, a deep network, one layer at a time. The problem of vanishing gradients was not a big deal in that case because we were training only shallow networks at the time. And then when we fit everything together, all we needed was to adjust, fine-tune everything, and then try to solve the original problem. So pre-training, the idea is that we are trying to initialize the network as close as possible to a useful combination of weights before we can start training. One reason why this works is that this initialization in a useful part of the space of possibilities is actually somewhat like regularization. We are confining the weights the network can reach to that region where they're potentially more useful. So initially it was thought that it was a way of trying to, for the network to converge to a different local minima, because there was this initial idea that depending on the initialization of the network, when we trained, the network would fall into a local minima on the loss function and then get stuck there. But actually this is not the case, because neural networks have so many parameters that they actually don't fall into a local minima. We just give up at some point, but the function could still be decreasing, and we don't, in practice, train networks towards the local minima. The thing is that probably pre-training allows the network to explore different regions of the parameter space. And this unsupervised learning will lead the network to try to identify regularities, identify the shape of the data, so to speak, and that helps find the right features. So this can work when we have poor representations of the data. For example, this here, one common example is word embedding from one hot vector. You have to describe what words appear in the text, but you need a vector of constant size to describe the word. So you can have a vector of 10,000 and you use one in one position to indicate that word, and the rest is all zeros, and this is a very bad representation, because all words are at the same distance from all other words, because each word is just a one with a lot of zeros. And so we can use this kind of unsupervised training to try to compute these embeddings, these representations in a more dense space, where the distance between words is more meaningful and represents words that are similar, things like that. This is a specific example from this human actions data set, which has 5,000 dimensions for the different actions, but mostly in all examples these are nearly all zeros. Only about 2% for each example are not zeros. And they train a denoising autoencoder on all the data, and the autoencoder learns a representation that when PCA was applied on this hidden layer, we could see some clear clusters of examples. So this was not evident on the original data, but the autoencoder learned a different representation where this became more evident. And with this, they actually won the competition for predictions with this data. Another case where it can help is by regularization. So we have, when we don't have much data, we can easily overfit, but regularization helps prevent that by constraining where the weights can go. So we make the model stiffer, so to speak. It cannot adjust so much to the data. And this was a paper with some exhaustive examination of what happens with and without pre-training. And what they did was for the complete test set, they concatenated the vectors of activations of the network. So you can imagine that for each iteration, at one state of the network, you pass the complete test set, concatenate all the activation vectors, and you have something with millions of dimensions inside. And then they use these algorithms for projecting from this high dimensional space into 2 dimensions, and they have some slightly different attributes. So distributed stochastic neighborhood embedding tries to preserve the distances to the close neighbors. So it preserves topology locally but not globally, and it allows us to see the details of the neighborhood of each point. And these points represent the first 50, they represent 50 networks, and the colors are progressing along the training. So they start at blue and they go to cyan and green and so on to indicate how much the network was trained. And these are trajectories for 50 networks. So basically, we see that without pre-training, the network starts more or less here. This is that random first initialization of the vectors, and then they seem to go in the same direction and then start to spread out and to slow down. And so here these tails are after more training iterations. The networks are only changing slightly. And this one was with pre-training. So even though, so these were initialized at random, these were initialized with pre-training, unsupervised pre-training. And so they start at a different region of the space of possibilities, and they spread out to different regions of the space. But with the stochastic neighbor embedding, we are not looking at the large scale. So this does not preserve distances at a large scale, only in the detail. And if we use isomap, isomap tries to preserve distances between the points over all the set. And here we can see that with pre-training, we're actually covering a much narrower region of the space of possible, of the parameter space. And they seem to converge roughly to the same region here. Whereas comparatively, if we start without pre-training, the networks spread out a lot faster. So we can see this pre-training as a way of regularizing the way the network learns by restricting where the network can look for the best parameters. So unsupervised pre-training is not very used today, except in some applications like word embedding and things like that. But it was what started deep learning before rectified linear units. So the thing is that with rectified linear units, there is no longer a problem with training a deep model in one go, and so it's easier to fine-tune hyperparameters and things like that than it is if we have to pre-train the model and then fine-tune it, because then we have two different stages for the same model. But in some cases, it's still useful, and in any way, for historical reasons, this was an important step. But there is something similar here now that we can apply to this problem of transfer learning. So, unsupervised pre-training, we are doing the pre-training of different layers of the network just as initialization. But we can do things differently where we already have a trained network and we use those results as a starting point for solving another problem. So this can happen if, for example, we have a different problem of classification, for example, but the lower level features may be the same. For example, suppose that we have a network trained to classify images in dogs, cats, horses, and things like that, and now we need to classify images in boats, planes, trucks, and so on. Although the problem is different, possibly at some representation level where we're looking at edges and colors and sizes and things like that, those features are equally useful for one problem and the other. So the idea here is to transfer that knowledge from the first, the network that was trained for the first problem, into the network that we are using for the second problem. We can also have shared representations at some higher level, and then what changes are the lower level ones. For example, for speech recognition, there are differences in the way people talk, which are small differences in pitch, in rhythm, and so on. But then there are some higher level representations of language structure and what words come after other words and so on that are the same. So in that case, it would be the opposite. We could take advantage of some part of the model that was pre-trained for the higher level and just train the part that's missing. Another problem where we could use transfer learning is in domain adaptation, where we want to model the same mapping from input to output, but the examples are drawn from a different distribution. For example, we train the model to try to evaluate or classify the emotion or the satisfaction of our clients from emails on, say, an online store, and now we want to apply that for a bank or an insurance company or something like that. So the problem is basically the same. It should have more or less the same features, the same kind of mapping, but the distribution of the examples are different, and that may require some fine-tuning, but probably we can start from the solution for the other problem and take advantage of that. So this is one example where unsupervised training can help a lot, where we are trying to deal with words and language because of the need to have very high and low density dimension representations of the text, and then embed that into something that is more useful. Another similar problem is when the distribution of examples is not different but is changing gradually over time. So if we have some model for predicting features of our customers in a business, as the economy changes or unemployment increases or something like that, there may be changes in the distribution of the people we are dealing with, and this may require the model to be adjusted. But again, this is not necessarily, does not force us necessarily to retrain the model from zero. We can transfer what we learned so far and adjust it. So basically what we are trying to do here is to use experience we obtained before into some new conditions, maybe a different problem, the same problem with different examples. The examples are changing slightly and gradually or something like that. There are also some extreme examples of transfer learning where we can do even one-shot learning or zero-shot learning, which means that our system learns with very few examples or even no example at all. This is strange, zero-shot learning, but I can give you an example of this. This is this paper for learning through cross-modal transfer. What we have is first, on one hand, an unsupervised, so unsupervised learning for creating a representation of words. So this is a manifold, a hypersurface in some higher dimension, where the words are spread out in a way that we can find words that are close together, say dog and cat, or truck and car, or something like that. In fact, these embeddings have some really amazing properties when we use unsupervised learning to create them. For example, if you start with queen and you subtract woman, for example, you get a vector from the two, from one word to the other, and then you add that vector to man and you get to king. So they keep this kind of topology of the meanings of the words, and they are represented in that space. So this was with unsupervised learning. They embedded the words in that topology, and then with supervised learning, they mapped from images to the words in that space. So you can have images of automobiles mapped to the position of that manifold where the automobile words were, cats or dogs in this case, horse, and so on. So this was supervised learning with a set of classes. The images were classified according to the words, and the network learned to map from the images to the space of the words. But now suppose we have a new image that belongs to a class that was never seen before. For example, a cat. There was never an image of a cat. But using the mapping from image to word, we get to a point in the manifold, look for the nearest word, and and it's close to cat. So the system, even though it never met a cat image in training, it can still map to the word cat because it has the mapping from images to the manifold. So this is one example of zero-shot learning, where the system actually knows about things it never saw during training. Another way of using supervised pre-training is, other than just taking advantage of previously trained models, is to break down the problem into different parts. So we can, for example, train just a few layers first with our data set. We don't get good results, but then we add other layers to the pre-trained layers and we speed up a bit the learning. Or we can train first part of the network with a subset of the examples, and then we add layers to the network and add the other example, so we have more classes or more complex problems to solve. We're going to do this transfer learning today. Last week you trained a convolution network for fashion NIST, and maybe you trained it in the lab or not, but if you didn't, I can give you the weights for the trained model. But the idea is that now we're going to start from that one. That one was trained on this data set. Fashion NIST has these images of 28 by 28 representing flows. And we're going to use to transfer from this to the NIST data set. So if you recall, the original model had some convolution layers, and then it had one hidden layer of 512 neurons, and then the 10 neurons for the output. What we're going to do is to use the convolution layers as they are. We are not going to retrain them, we're going to fix them, and then just replace the end part of the network and train only that part using the rest of the model without training. So we're going to take advantage of the similarities between things like detecting edges and the color changes and so on that the convolution network learned on this data set, and we're going to apply that to this data set. Another thing we're going to do is we're going to use the functional API for Keras instead of the sequential one we saw previously. The sequential API is practical because you just create a model and add layers, but it's a bit limited because you can only stack layers and it's not very flexible. So it's useful to know the functional API too. What we're going to do is create the same graph as the model we trained last week. So if you trained your own model, just adapt the same code. The idea is that you have the same computational graph, because then you're going to load the weights from the trained model into that graph. We're going to do just some simple changes, which is to name the layers that we care about, because then it's easier to just plug in that part of the model into the new model. So we're going to disable training for the weights on the layers of the previous model, and then recreate the dense layers, the multi-layer perceptron on the new model, and train that one on NIST. So to do that, you import Keras and the different layers that you need. This is the same thing as you did with the sequential interface. But for the functional interface, this part is the same. We need to reshape the images to feed them into the convolutional layers. But it's the same as you did last week. The only difference is that now we're going to load the NIST data and not the fashion NIST data. So we are going to use this new data set. Now, for the functional interface in Keras, what we do is we use the layer classes. We create these instances, these objects for the layers. But these objects are callable objects. They implement these call methods, so you can use them as functions. And what we do is, for example, here, we create a convolution to the object, and then we call this object giving the inputs as arguments. And this function, this object which works as a function, will return a tensor which is the output of that operation. So this way we can chain tensors together. So we get, from the inputs, we get the layer, we feed in the layer, in this activation we get a new tensor. We can just replace the variable because we don't need to store all the different variables. The chain gets stored by the function. Oh, it's learning on its own. So this way you can chain the different tensors together in a way that is similar to what we did in TensorFlow. So if you have different branches of the model, you can concatenate the tensors and then feed them into the next layers and so on. You have lots more flexibility than with the sequential model. What we need to do here, different from the sequential model too, is we need to start from this input object, which is similar to the placeholders that we used in TensorFlow. So this is the starting point, the starting tensor. We get this tensor and we feed into the layers, and we create a chain of layers by using each object as a function giving it the input tensor and receiving the output tensor. So this is the same architecture as last week, and it continues here. We're going to do here a little trick, which is to name some layers, because this makes it easier to find them in the model. Actually, you can just find them by index, so if you look at the complete model, you can count the layers, but this makes it simpler. So we're going to name the first layer the input layer, and the end of the convolutional layer, so the model continues up there. When we flatten the output of the convolutions, we're going to name that with another name, for example, features. So this is the old model. To create a model with a functional API, we chain together all these tensors and operations, and then we create a model object where we specify what tensor is used as the input and what tensor is used as the output. And since the Keras kept track of all these chaining together, it knows what graph we're using from this point to this point. So this is the old model. We compile it. It doesn't matter what optimizer we use because we're not going to train it. It's just for compiling. And then we're going to load the weights of the fashion NIST. So if you can use the .h5 format, which is the one we use for saving, you just add .h5 there. If you cannot, because some people don't have the library for that and need to save and load in TensorFlow format, you just leave out the extension, because the TensorFlow format uses several files and it needs to load those files. If you have your own weights from your model, this part will be exactly your model and you load your weights. If not, then you download a zip file I've placed in the page with the weights and the code for the original model that you can adapt to the functional API. And now we're going to do this. This is layers is just a list of pointers to the different layers in the model. We're going to iterate through all of them and disable training for them. So we set the trainable flag to false, which means that if we use these layers in training, they will not change the parameters. And now we're going to build the new layer. So we start with the dense with 512 neurons, but we're going to get as input to this layer the features layer of the old model. You see here the one that's at the end of the convolutional layers. And then we add the rest of that multi-layer perceptron, the dense part, and we create a new model which gets as input the inputs for the old model, and as output this layer. So what we're doing basically is we are creating a new model that starts the chain with the inputs to the old model, but then branches off at the end of the convolution layer into this set of layers. The old model is frozen. It will not change its parameters because we froze all the layers, but these ones are not frozen. So these ones will be trained using as input what is coming out of the convolution of the other model. So now you just choose the number of epochs and compile and start training. This, after the first epoch, you already get 90-something% accuracy on validation, and it's faster to train than the other one. But if you want, you can compare, because you can just create this whole model and train it on NIST and compare with what happens if you use the previous way and transfer learning. So I actually tested this, and there is a difference. So otherwise we wouldn't be doing this. So this would be for transfer learning. You'll notice if you ask for the summary of the model, you still have lots of parameters to learn, because most parameters are here in the dense part of the network. The kernels don't have so many parameters, but you have these 60,000 parameters that are frozen and will not be learned. Some of these are the batch normalization parameters, which are not learnable, but many of them are the kernels for the convolution network. The other exercise is simpler. You're just going to use, the functional interface. We're going to use the UCI banknote dataset from the first tutorial. This is an example of an architecture that works. So I used 16 neurons, 8, 2, 8, 16. Then this for is necessary because we have 4 input values. So at the end of the autoencoder, we need 4 output neurons. And since this is a regression problem, we are trying to fit as close as possible to the values we are receiving. These will be linear output neurons. But this part is fixed because this is just the dimension of the data. This part you can change, and the 2 on the neurons on the middle are also fixed because that is the dimension we want to reduce the data to. So I tried this with the ADNE optimizer, with this learning rate, leaky ReLU, and this architecture, and I got these results. So this is PCA, and this is the projection using the autoencoder, which separates the data better. But what I would like you to do in this case is to play around with the architecture and get a feeling for what happens if you try to make it too small and then you cannot encode properly, or you make it too large and then it's too flexible and the results are not very good in the middle. So this may take some time. I don't know if you have time in the tutorial, but if not, you can continue at home because this is just fiddling with the parameters to get a feeling for what happens. Okay, so to sum up, we saw this idea of using, learning some representations, either unsupervised or supervised, that can then help us get the right features for solving our problems. Okay? So this we can use to transfer learning for one example to the other, or even to learn some mappings that can then be applied to new examples that don't even fit the classes we trained in. Okay? So this chapter 15 is about this representation learning, and 874 talks about supervised pre-training specifically. So you can look more details there. Any questions?